In the previous two videos, we were using TensorFlow to solve the linear regression problem. We looked at several different solutions using TensorFlow, including the linear algebra solution by solving the normal equations. The batch gradient descent method and also the mini batch gradient descent method. And all of those methods can be implemented using TensorFlow. But the purpose of studying the linear regression problem is just to demonstrate some key concepts and also to show some of the capabilities of TensorFlow. The problem that we are actually interested in solving is the MNIST handwritten digit recognition problem. And a more detailed description about the MNIST problem can be found in the 8th video of this sequence. If you have background in statistics, you probably already know that this MNIST problem is actually one typical example of the so-called logistic regression. In fact, this MNIST problem is so famous and also so straightforward to code up in TensorFlow. The training and the testing dataset are bundled with the TensorFlow distribution. And you can also find example solutions to this MNIST problem from TensorFlow's official tutorial website. So if you haven't been there before, that's the web page, right? So all you have to do is to actually navigate to the homepage of TensorFlow, right? And then you have a link to the develop, right? And then you have getting started, right? Getting started with TensorFlow, and then MNIST for ML beginners, right? And it's going to provide a code solution, for this particular problem, right? And it's actually providing quite a few solutions, right? You also have deep MNIST for experts, right? So this MNIST solution for beginners is going to provide you with about 92% of a correction rate, accuracy, right? And then using the deep MNIST, you can improve the accuracy to like 98% of them, right? Depending upon your implementation, depending upon how you actually implement it, right? And you can also find solutions of the MNIST problem from, for example, typical textbooks about TensorFlow or textbooks about machine learning or deep learning, right? So this MNIST problem has been used as a typical example for deep learning from various learning sources. The solution I'll be writing both in this video and also in the next, if I can finish it in the next video, right? The solution I will be writing has no inherent differences from the solutions provided at either TensorFlow's tutorial website or other textbooks, right? But what I will try to highlight in this in the videos is actually the similarity between the solution for the MNIST logistic regression problem and the solution that we have written for the linear regression problem. And we finished writing the linear regression the solution for the linear regression problem in the last video, in the previous video, right? I will try to highlight the similarities. In fact, both the structure and almost the majority of the code, and the majority of the code are in fact almost identical to our mini batch implementation of the linear regression problem, right? Both the structure and also the majority of the code, except for maybe a few lines for computing the MSE, right? For the logistic regression problem, it's not using just a summation of the squares of the error, right? it's actually using the so-called cross entropy. Again, it's a concept that we discussed very briefly in the 8th video. Right? It's so the calculation of the error or the calculation of the loss is going to be different. But it's also provided by a existing TensorFlow function. You can implement cross entropy calculations using existing TensorFlow codes. You don't really have to write it by yourself, right? And pretty much that's probably the most important differences. And then all the rest of the codes are very similar. And in our mini batch gradient descent solution for the linear regression problem, we actually spent lots of time to talk about how to actually generate those kind of fake data set with like 10,000 examples in it, right? 10,000 training examples in it, and we also talked about how to write a function that's called a fetch batch, right? This function, the purpose of this particular function is just to fetch data from this fake data set to fill up each mini batch, right? To fill up the placeholders basically for each of the mini batch, right? But in the mini batch gradient descent solution for the MNIST logistic regression problem, we don't have to prepare the data set by ourselves. In fact, the entire data set has been very well prepared and organized by the TensorFlow team, and all we need to do is to import a Python module, and then just use a function in that module to download and sort of organize all the data on our disk. So the first thing we're going to do is to try to import data, and then let's take a look at what the data looks like, basically. So we're going to import TensorFlow, right? And then we're going to import the data set for our MNIST sort of problem from TensorFlow examples, it's a plural, and then tutorials, and then MNIST import data. And then we're going to use the input data object to actually read the data set, right? So MNIST, this line is going to actually download and organize the data for us. Input data, read data sets. And then this particular function, this particular method defined on the input data is going to take two inputs. It's going to take two inputs, two mandatory inputs, basically, Right? No, it's just actually just one mandatory input. This one hot is also optional. This is a keyword argument. That's also optional. The only mandatory input is just this particular string. So the first string input to the read datasets method is the path or the directory where we would like to store the downloaded datasets. So it is not a huge dataset. So with all the training and the testing data included, it's actually less than 20 megabyte. Right? So let me open a new terminal. I myself have actually downloaded the dataset. Right? Machine learning, MNIST. Right. So these two files, you might have noticed it ends with .gz, which means that it has been zipped. It has been compressed. So all those data are compressed data actually, and the read datasets function can actually read those compressed data. It's not a problem for it. Right? It has the capability to read those .gz files directly. You don't really have to unzip them. Right? You don't have to unzip them. These are the raw files downloaded by this particular method actually. So you can sort of take a look at the size of those files. So this is actually the training dataset. Right? And then this is that's the training dataset. It's training input dataset, which are the images, the handwritten digits. Those are the images. And then this is for the labels. Right? That's sort of like the ground truth for each of the image. Right? Each of the image is just a handwritten digit. These labels is gonna be the ground truth for what the digits are. Right? Suppose you have a handwritten 5, and inside of the labels, the corresponding number is going to be 5 for that particular image. Right? And then these two files are for the test dataset. Right? We haven't been actually careful about training dataset and test dataset in our previous toy examples. Right? We haven't actually talked about the distinctions and how to use those, how to partition and how to use those different datasets in the correct way yet. But later on, when we sort of trying to deal with realistic examples, we will talk about those things more carefully. And that's basically just those 4 files. Those are just 4 files. So if we have not downloaded those data from the MNIST website, right? All those data are actually hosted at the MNIST website. It's actually quite it's a quite important website. If you just Google it, you're going to be able to find that website, right? And the read datasets, this particular method is gonna download those data for us automatically, so we don't have to manually download them. So this particular Python function is gonna go to that website and download those data for us, and then it's gonna store the downloaded data inside of this particular directory, right? Whatever you specify in here, right? It doesn't have to be this particular like what I'm writing here. And then if we have already downloaded those data by ourselves, for example, right? If you have tried this particular data set before in some other kind of opportunities, and you have stored them inside this particular directory that you are given here, right? Then this particular read datasets method will not try to download it again. It will just try to use or read the data that you have already downloaded. So it's going to do a check. So it's going to check this directory, see if you have those data already. If you don't have those data, it's going to go to the web and download the data for you. And then the second argument, the second keyword argument, one hot equals to true. This argument is basically telling the method to convert all the labels in the training and the testing datasets to the one hot encoding. So if you have no idea about what one hot encoding is, I have a very brief explanation about this one hot encoding in the 8th video of this particular sequence. It's basically just so if you have like a classification for like 10 situations, right? Because you only have like 10 digits from 0 to 9. It's like 10 digits. It can be only one of them, right? It cannot be both 0 or 9, 0 and 9. Right? It can be just one of them, one of those 10 situations, right? And then if the label gives you a 5, then this for these 10 elements, you're gonna have a 1 at the 6th position, right? And then every other position is gonna be 0, right? But if your label is has a value of say 7, then you're gonna have a 1 at the 8th position, and then every other position is gonna be 0. So that's what one hot encoding actually does. It just converts like one label, the label with one value, to like a vector of 10 values, right? and 9 of those 10 values are going to be 0. Only one of those 10 values, only one of them is going to be 1. So that's one hot encoding, and the position of that 1 is determined by the label. So basically the labels are essentially just like the ground truth vector, right? Just like the ground truth values we were constructing the linear regression example that we were looking at in the last video, right? But here in the linear regression example, the ground truth was constructed as a fake data set, right? It's actually it's a fake data set. It's not real. But here in the MNIST data set, all the ground truth values are actually real. They are actually real ground truth. But now every ground truth is not a single value. It's not a single value anymore. But every ground truth is a vector with 10 elements, and one of those 10 elements has a value of 1, and all the remaining 9 elements are zeros, basically. So if we would like to sort of examine the content of this returned MNIST object, then we can sort of do something in the console. But let's run this piece of code first. In fact, I have already downloaded all the data, so it doesn't have to sort of go to the web to download data again. So it's just going to extract all the files. So now we have a object here, right? MNIST, and it's got a type that's called a data set, or data sets. It's not just a one data set. It's got data sets. It's got like 3 of them in it, right? So the size is 3, and you will see why it's 3, because it's got a training data set, it's got a validation data set, and also a test data set, right? So if we would like to sort of examine the content of the returned MNIST object, we can use the dir command. Right? If we just type dir followed by with MNIST in the parentheses, you're gonna see lots of system provided things, right? All those names that starts with this kind of underscore, underscore, right, or double underscores, right? These are not really sort of provided by. These are all some kind of a system functions or system names, basically. So if you want to get rid of those things, you can do a list comprehension. If you have no idea what list comprehension actually is, you can take a look at my hands-on start to Python sequence, and in the third video, in that particular sequence, I talked about list comprehension in Python. So for name in dir ms and istf not name dot starts with underscore, right? And then it's going to create a list for us. So count, index, test, train, and validation. Right? We see all those attributes from that particular object. Right? So the entire MNIST dataset is contained in the test, train, and validation. Right? So basically, they have partitioned all their data into like these 3 sub-datasets. Right? We haven't actually been very careful about partitioning our datasets into like 3 sub-datasets called test, train, or validation in our previous examples, right? That's because we were mainly just using the linear regression as a toy problem to study TensorFlow. For any kind of realistic problems, such as the MNIST logistic regression problem, it's actually extremely important to partition the entire dataset into the 3 sub-datasets, actually. These kind of 3 sub-datasets. And we will discuss the reasons for doing that in future videos. But it is very, very important to do that, right? It's very important. And if we would like to actually examine these 3 sub-data sets, say let's look at train this sub-data set first, right? So we can do the same thing basically. You can still use a comprehension, right? But this time train, right? MNIST dot train. Let's look at what's actually inside of it. Right? We've got a few things. Epochs completed. Images, labels, next batch, num examples. Num examples should the name for this thing should be quite evident, right? That's the total number of training examples in this training dataset, right? So we want to sort of look at it, right? 55,000. We're supposed to have like 55,000 training images and also the corresponding labels, right? One hot encoded labels, basically, right? So epoch has completed, right? So that's basically a counter for counting how many epochs or how many rounds we have gone through the entire training dataset. For now, it's supposed to be like 0, but I did some training before, but I'm not sure if I cleared everything. Yes, right. Epoch is completed. For now, it's like 0. But suppose we have started our training. If we have finished writing our code and started training, then this number is going to keep increasing as we iterate through all the epochs, basically. Right? It's a number, basically. And then we have another function called a next batch. This next batch function serves exactly the same purpose as the fetch batch function that we wrote by ourselves last time when we were solving the linear regression problem. Next batch is going to return the data that's going to be used to fill up the next mini batch. It's going to be used to fill up the placeholders, the TensorFlow placeholders for every mini batch, right? And last time we were implementing this particular function by ourselves, by hand, right? But now TensorFlow actually provides this function for you. So all we have to do is to basically call this next batch function to fetch the data for every mini batch, basically. And that's the function that we're going to use, right? So we need to pay attention to this particular function. We're going to use it when we write our implementation, our solution, right? And then the input image data are going to be stored inside of the images, right? So if we can find out the type of this particular data structure, so we can just type MNIST.train.images, right? It's going to tell us it's actually a NumPy array. It's an ND array, so it's a NumPy data structure. It's basically it's actually a 2-dimensional array. So if you want to check out the dimension of images, you can type ndim. It's going to tell us it's a 2-dimensional thing. If it's a 2-dimensional thing, then it means that it's a matrix, basically. So the images is going to be a 2-dimensional array, and we can try to find out its dimensions in the the size in the 2 dimensions by looking at the dot shape. So it's going to tell us it's got 55,000 rows and 1,784 columns. Right? 55,000 rows, that's kind of understandable, right? Because we looked at the number of training examples. That's 55,000. So every row corresponds to the input image for one training example, right? And then why 784 columns, right? Why? Right? Because every image is actually 28 by 28 pixels, and we have inside of this particular data set, they have actually flattened that 2-dimensional 28 by 28 pixel image into a 1-dimensional vector, right? So if you multiply 28 by 28, you're going to get 784 exactly, right? So 784 is actually a flattened out 2-dimensional image with 28 pixels by 28 pixels. Right. So every handwritten digital, every the image of every handwritten digit is a 28 by 28 pixel image, basically. Right. We can also sort of look at the total number of images in the testing dataset, right? Which is not train but test. Right. It's 10,000. Right. So the training dataset has 55,000, and then the test dataset has 10,000. Right. This is kind of a typical proportion, basically. It's a quite typical proportion, about 1/6. So the test dataset is about 1/6 of the entire training dataset, right? And then if you want to look at the validation dataset, right, it's 5,000. It's 1/10 of 55,000, about 1/10. So validation. What exactly is the distinction between validation and test, right? We're gonna look at these kind of sort of differences later on, in later videos, right? Maybe not in today's video, but in later videos, in tomorrow or the video after tomorrow's video, right? So and then we can also sort of look at the shape of the labels, right? So MNIST train dot labels dot shape, right? 55,000 rows, 10 columns, right? The reason that it has 10 columns is because every label has been converted into one hot encoding, right? So suppose we change the one hot equals to true to one hot equals to false here, right? And then let me just do a reset. And then if I run this code again, and now if I check the shape of labels, then it's gonna be 55,000, right? It's not gonna be a two-dimensional thing. It's gonna be a one-dimensional thing. If you check the dimensions, it's a 1. It's not a two-dimensional thing here. Here it's a two-dimensional thing. It's a matrix. But here it's a one-dimensional array with just the 55,000 numbers because it has not been converted into one hot encoding yet, right? So we need to sort of remember to set one hot to true in order for the code to work, actually. So, right. Before we start to write the code for building the graph, let's define and also set the values for the 3 hyperparameters: the learning rate, the number of epochs, and also the batch size. So here it's we have finished importing the data. Now let's try to write the code for hyperparameters. Right. So here it's import data. Here it's let's define hyperparameters. So we have 3 hyperparameters, and we have used all of them in our linear regression example, right? And then epochs equals to, let's give it like 60, and then batch size equals to 100. So we used these 3 hyperparameters in our linear regression example, right? So if you don't exactly remember, we set the learning rate. Where's the learning rate? So we set the learning rate in our linear regression example to 0.01, right? And then here we're actually using the same value. We're setting the learning rate to 0.012, right? And the number of epochs we're going to go through, so all the training examples, every training example inside of the training dataset is going to be examined by the neural network for like this many times, right? And in the linear regression example, we are looking at we have the same hyperparameter, but it has a different name. It's called n_epochs, right? But here we are using probably a more informative name, training_epochs, right? Here we have a value of 70, but here let's use, we can certainly set it to 72, but let's just change to 70, right? Let's see how it's gonna work. But in fact, we only need like 60 apples to actually reach 92%. So, and then in the linear regression example, we also had a batch size, right? Batch size equals to 100. Here we also have batch size equals to 100. Right? And we will also need two variables to store the dimensions of the matrices and the vectors, basically, right? So nCo is going to equal to 784, and then nClass is going to equal to 10, right? So here nCo, which has a value of 784, which is basically 28 pixels multiplied by 28 pixels. This is the number of columns. This is the number of columns in the input image dataset, right? Both the test and the input image dataset. That's the number of columns. Right? And then the nClass is the number of columns in the ground truth output. That's the labels, the one-hot encoded labels, right? Because we have 10 classes, right? We have 10 situations for the label. Right? The label can be just the 1 out of 10 possibilities, basically, right? So that's called the classes, the number of categories, the output can be, the label can be, basically, right? And that's sort of the column number of the labels, the one-hot encoded labels, right? And after we have finished writing the hyperparameters, now we can start to build the graph, right? But we will leave the code for tomorrow.